Okay, good afternoon, everyone, and good afternoon to those on Zoom. Basically, we're gonna have our second tutorial of RCAIDE. Does someone turn on the screen projector? Oh, thank you. So basically, last tutorial, we covered, how to, well, the first tutorial we covered how to install RCAIDE, and hope everyone has it installed. If you don't, like I said, we can watch the video, the first video that will be uploaded, or you can just see me afterwards. The second tutorial, we covered a Boeing 737 oh, hi, Professor Ansel. We covered a Boeing, hey.
I was like, I should head down. I'm trying to finish this paper first
Oh,
and
no,
an email, but I'll
yeah.
head down soon.
Okay, cool. The second tutorial we covered Boeing 737 simulation. And this tutorial, I want to actually go into that simulation and hopefully explain to you the architecture, right? Because all we did the last week was basically I went through that single file that has in everything from vehicle geometry to mission simulation setup to the analysis setup to what else? So you guys see the general main file, right? But that's really good for, I would say, most people who are doing simulations, high-level simulations, or just using the code. Because we're doing a lot of development in our group. And if anyone online or on YouTube wants to do the development, we want to understand what is really going on under the hood. So today, hopefully, I want to explain to you all basically how the network is set up. I spent some time talking about that last tutorial, but this time I really want to go into detail on the architecture of the network. And I'll try to see if I can draw it with my iPad. And then afterwards, I will try to do it. I'll show you it in code. Okay. As I get that set up, are there any questions so far? Any comments, any thoughts before I move to code? Okay, awesome. Let me first. Okay, perfect. So while the Zoom is warming up, I'm going to join. I don't want to switch, I want to join. Let me join with my iPad. 1 second. Okay. Just gonna join with my iPad. Oops. Okay. I wonder if I switch my screen, will it still record? Does anyone know that? If you switch your screen, will it still record? Yeah, okay. Let me see if I can just join. Okay. Let me go to my computer and find the meeting invitation. Does anyone know the meeting number by hand or off the invitation for this Zoom?
I can dig it up right here. I'll put it in the chat.
Thank you. I want to join on my iPad at the same time so that I can sketch out some things on my. Yeah, the meeting ID. That's what I need.
Meeting ID.
Yeah. Oh, thank you.
Yep. And I can give you the passcode if you need it.
Okay, I'm on. Awesome. So the first thing I'm gonna do is that I'm actually gonna draw out the I want to actually draw out the network itself because, like I said, Arcade is a little bit different than Suave. And as I was telling you guys last week, basically, we made a lot of fundamental changes in Arcade so that we can model hybrid propulsion systems. We had a discussion about fuel tanks, somebody from Professor Ansel's group about hydrogen fuel tanks last week. I guess he's not here today. Also, we talked about failure modes and how do you model partial failures, which is pretty interesting at a conceptual design level, right? And I don't think any other software can actually do that. So that's something we're really focusing on in this tool. So the first thing I'm gonna do is actually I'm gonna draw out what we coded last week, and then we're gonna go into the actual network itself. Okay. All right. So let me first stay as co-host and share my screen. So I'm gonna share my whiteboard. And then I'm going to put this here. Right, so everyone can see my screen? So let's start off with the definition of an aircraft. So in Arcade, we define, oops. Yeah. You have a vehicle. See if we can write sideways. Okay, so we have a vehicle, and this vehicle has different components, right? So we have a fuselage, we have wings, what fuselages, wings, you can have networks, you can have nacelles, you can have a whole bunch of other different things, right? And remember last time we actually talked about defining those individual components, right? This is the one I want to go inside of. So this networks is pretty interesting because in Arcade, we can model different types of networks, right? What are the types of networks we can model? Electric, hybrid, there's turbofan, there's turbojet, there's scramjet, there's ramjets, there's a whole bunch of other things in there you can model. Today I want to focus still on the turbofan because I want to really go into how this turbofan model is being defined. Okay, so let's look at this turbofan model. So for trying to do it in a different color this time. For a conventional aircraft, a 737, right? We are going to model it with a turbofan network. Okay, so the network is called network. It's a turbofan engine. Right? And this turbofan engine network essentially has on its network something called fuel lines, right? And a fuel line is a type of distribution. So the network, one layer down from the network, and I'll try to draw in a gradient of a color, is the distribution, right? And for a turbofan, we have fuel lines. So we model everything in the turbofan network inside of classes called fuel lines. And the reason we do that is because we want to be able to, if hypothetically you want to have multiple independent fuel lines, you can't, right, on this network. Does this make sense to everyone? So, but for our case, we only have one of these, right? We only have one fuel line, but you really can model multiple because fuel lines is a class, right? And one step below the distribution, we have what? Propulsors, right? So propulsors pretty much are anything that generates thrust. So in this case, the propulsor is the actual turbofan itself. Make sense? So on a fuel line, and I showed you this, remember I showed you last week a paper that myself and Professor Ansel and some other folks are writing, and it has a distribution. Basically, we have one fuel line and we have two propulsors, right? So you can have multiple propulsors on a network. I mean, on a fuel line. So you can have, let's say, a 747, right? A 747 aircraft has 4 propulsors on one fuel line, right? And the reason we want to do that is such that if you have, if you want to model a failure mode of the aircraft whereby one propulsor is not working, you essentially can channel the fuel on that fuel line to the other propulsors. Make sense? Make sense, everyone? Cool. So, but in addition to propulsors on a fuel line, you also have this guy. You have things that pretty much can store energy, right? So you have, let's call it, well, particularly for this distribution, we have, let's say, fuel tanks, right? So on an aircraft, you can have multiple, similar to how you can have multiple propulsors on a distribution line, which is the fuel line. You can have multiple fuel tanks on a distribution line. And this now allows us to model things such as like the Concorde that has 9 different fuel tanks on one distribution line, but it only has 2 propulsors, which are turbojet engines. Does this make sense to everyone? All right, so now we're actually going to now dive into the code itself so you can see what is really going on under the hood. Make sense? All right, cool. So I'm gonna share my screen. So stop sharing my screen. Stop share. And I'll share the screen. Oh, I probably need to share it via Zoom too. So share screen, desktop too, share. So, okay. So we're not only going to cover the Boeing 737, we're going to cover the actual network script itself. And the reason we're going to cover that, first of all, can folks online, can you see my screen?
Yes, we can. At least.
Okay, awesome. So we're not going to cover again, and the reason why I'm going to go over this one more time is because I think there's value in repetition, but also I think that this is a great place to start off before we go into the actual turbofan engine network script. And the reason why I want to go in that script is because for the folks in this room who are modeling new energy networks, from hybrid propulsion systems to all electric aircraft to whatever you want to model, I think I'm going to go directly to talk about the scripts that are really beneficial to you, or the ones that you're probably going to be editing the most. Okay. So let me first increase my window, zoom on this again. Where's the zoom tool? Edit. Ah, thank you. Oh, I think it's just shift and yeah, awesome. So we covered this script before. I want to go into this script. So we talked about the vehicle setup, configuration setup, analysis setup, mission setup. We talked about all this in the previous video. If you want to see it, go on YouTube. But what I want to cover again is the turbofan engine again, right? And we'll start from here and we go inside the turbofan script itself. So the cells. Okay, so once again, the turbofan engine is the network, right? The network has on a distribution called a fuel line. But if you're an electric aircraft guy, the distribution, you will have arcade.energy.networks.distribution.electrical bus, right? I'm just using the fuel line distribution system for this tutorial. So I define a fuel line, and I'm adding only one fuel tank on this fuel line. So I define my fuel tank, right? And I'm going to add it onto a class called fuel tanks, which is on the fuel line. So this aircraft only has on one fuel tank. Not realistic, but it's just a tutorial. And then I'd first define my propulsor. So I define a propulsor, right? And in that propulsor, I'm going to put inside of that propulsor class one turbofan, okay? Because you can also put in that propulsor a motor and a propeller, you know, etc. And I'm going to append that propulsor to the turbofan. Sorry, I'm going to append it onto the propulsors, onto the fuel line itself, right? So now that fuel line has on a propulsors class, right? That has in right now only one propulsor called a starboard propulsor. Make sense? And I pretty much copied that same propulsor over, and I stored it also in the propulsors class onto the same fuel line, right? So now I have one aircraft with one network having one fuel line. That fuel line having two propulsors and one fuel tank. So now for a hybrid system, you can have, well, I guess we're not developing hybrid systems, Edwin and I, but basically, let's do all electric. For an all electric aircraft, you can have multiple batteries on one distribution line, which we call an electrical bus, right? So you can model now battery failures. If you have multiple hydrogen fuel cell tanks, you can model that by putting those hydrogen tanks on one hydrogen distribution line. So if you have any type of failure, you can pretty much model let's say if you have a tank failure or a propulsor failure on the same line itself. Does that make sense? Okay, cool. So let's actually go back and explore what I really want to talk about today, which is this turbofan engine network. So if within RCAIDE, there are several different networks, and we're constantly developing new networks. Currently, I'm developing hybrid, series, parallel, and series hybrid network. So we're developing a few different networks, but let's talk about a very simple network called the turbofan engine network. This turbofan engine network inherits from a base class called network, right? It's just a base, it's a base class. And this network, pretty much, if we were to click in here, how it's defined, is this defined as the energy component that having the types of distributors, right? It's an empty class, right? It having buses and fuel lines, etc. But we're only going to use fuel lines in this case, right? So let's go back to this turbofan engine network. So in this network, have some small defaults with the tag of it, which is pretty much the name. But then the real thing I want to talk about today is this evaluate thrust, right? And this evaluate thrust is the most important function within this turbofan network. It is where the magic happens every single time step, okay? So within this evaluate thrust, what we're going to first do is that we're going to unpack the conditions, the state conditions. And the state conditions are things such as such as the airspeed, density, altitude, everything that you need to calculate the thrust on the generated by the turbofan, right? So we pull out the conditions, And in line 91, I'm basically just compressing what I'm really going to use in this script. So I'm going to take out the fuel lines because I want to explore what's in that fuel line. Remember, the fuel line itself having what? It having the propulsors and the fuel tanks. So I'm going to look at, I'm essentially going to take this fuel line class and explore it in a for loop. And this script reads, for every fuel line on the aircraft, and when I was coding the script, I made sure, like I said, the reason why I did this is such that if some arbitrary person wanted to have multiple types of fuel lines on an aircraft, you actually can, right? So for each fuel line, right, it first goes in here and checks and see if the fuel line is active, right? If you have an active fuel line, right? And then if the fuel line is active, it looks to find all the tanks that are connected to the fuel line, right? Because you can have multiple different, you can have, like I said, for the Concorde, you can have 9 different tanks on the fuel line, right? So it first collects your fuel line tanks, and then it pretty much does this line 100. And line 100 is the most important line in this script. Line 100 is where everything is calculated, right? It calculates the thrust, the power, and the mass flow rate of the turbofans that are currently on the fuel line, right? So it takes in the fuel line itself, right? And it takes in the state. Why does it take in the fuel line? Because remember, the turbofans are within the propulsors that are attached to the fuel line. Make sense to everyone? Okay, so if I explore this propulsor, this turbofan propulsor function, so I just went into the turbofan propulsor function, it basically goes through, on that fuel line, it loops through all of the propulsors on that fuel line. So if you have a conventional turbofan engine, it loops through both propulsors. So it says here, for every propulsor on the fuel line, right, it pretty much computes the thrust. So the way how to read the script is that if the fuel line is identical, and if the propulsor is not the first one, right, it pretty much just uses a previous calculation to store the results, right? I wrote the script. I was talking to Edwin earlier. I probably should change the format of it. But basically, when you first go through this script, this index is 0, right? Is the first propulsor. So it actually jumps here and computes the properties of the ram, the inlet nozzle, the low pressure compressor, the high pressure compressor, the fan, the combustor, the shaft, it goes to the shaft, then it goes to the high pressure turbine, low pressure turbine. It pretty much computes every single property along the turbofan, right? And it stores pretty much the results right here, right? It stores the mass flow rate, the total power, and total thrust. So the first time you go into this, the first time the loop runs, it skips the first part and it does the second part where it actually computes all of the turbofan properties. Does that make sense? Now, how many engines does this aircraft have? 2. I have 2 engines, right? So this is only the first propulsor, so it's going to go back to the top and loop through the second propulsor, right? Make sense? However, instead of running this calculation again, right, because it's an identical propulsor, and you're not at the first one, you just save the results from the previous propulsor onto your propulsor. It's the same engine, right? And you just essentially update the total mass flow rate, total power, and total thrust. And the reason we do this is because if you think about it, for example, if you have, do you know how actually aircraft engines are tested? I think I already told you, but basically, so imagine if you have a 747 aircraft and you want to test a new aircraft engine, right? You can actually simulate it in Arcade because you just turn off that identical propulsor, make that false, and essentially what you're doing is that you're going to run the aircraft, right? And for the the new turbofan engine, you're just going to recalculate the properties based on that new engine. So now the way how the script is written now, you can actually calculate the performance of an aircraft with maybe one new type of engine on it. Right? See the power in this script. It's still, in talking today, I realized that we can still do a little bit more to make it more clean, but that's the gist of it. That's the new power of having this level of code. Is that clear to everyone? Okay, so instead of rewriting the script, like I said, it just essentially doubles it, right? So once it's finished, it returns back to the turbofan engine network. And now you have here, for each fuel line, you have all of the thrust that is produced by all of the propulsors. You have all the power that is, the shaft power. And then you also have the total mass flow rate that's consumed by the aircraft engines. So we have total mass, the total amount of fuel the aircraft needs. Now, what we need to do now is think about, okay, where does this fuel come from, right? Because remember, this aircraft, although it has one, it can have multiple fuel tanks, right? So this next line here basically goes through each fuel tank, right, on the fuel line, and then using a fuel selector ratio, right? So this is another feature that I mentioned last time. What we did is that RCAIDE is trying to model new systems as realistic as possible. So we're adding a lot of different features to how energy flows within a system so you can regulate stuff, right? So here I'm essentially regulating the ratio of how much fuel is coming from one fuel tank to the other, right? So because this aircraft only has one fuel tank, obviously this fuel selector ratio is what? It's just one, right? But you can imagine for the Concorde, you can actually regulate the fuel ratio from each fuel tank, right? And then if you are doing such things like aircraft stability, and you know where exactly the fuel tank is located, you can actually optimize how the fuel is being regulated per flight segment based on literally an array of numbers, array of ratios, right? So like I said, know that you're modeling the fuel tanks as separate entities, and you can store the location of the fuel tank on the data structure called fuel tanks, which is on the data structure called the fuel line. You can actually model how the energy is being flown, and energy is being passed through different fuel tanks. Make sense? So after that is computed, then you pretty much can compute. Well, you already have total thrust. You just add up this, all the thrust on each fuel line, and then you just pack it and send it back to the mission solver. Any questions so far? Okay, so what I'm gonna do right now is that I'm going to, like I said, these are practical tutorials. Obviously, there's a lot of information on the coding the RCAIDE code repository, and I think that stuff you can look for in a PowerPoint tutorial or a PowerPoint spreadsheet on exactly, where the files are located. I think these tutorials are meant to give you a practical understanding of how the tool is actually operating, because, I mean, everyone here is probably going to be doing some code development, right? So you need to know how stuff is being run. Make sense? Yep.
Does it actively decide as to how much fuel it's going to take from each fuel tank?
Good question. So the question was, does it actively decide how much fuel is being taken from each fuel tank? So we model things in mission segments. So you could theoretically add, because now the fuel selector is an actual value, you really could theoretically put that value in the optimizer and optimize it during the actual segment.
On the basis of the weight distribution.
On the basis of weight distribution, because you're getting the time history of the fuel, of the fuel consumption, right? So you're getting a time history of the aircraft weight. Therefore, if you have the aircraft weight as a residual in your optimizer, you can optimize that fuel selector ratio for each fuel tank to determine how exactly the fuel or hydrogen, liquid hydrogen, whatever you want to do, right? On an aircraft to optimize it for maintaining stability. So theoretically, yes.
Which part?
For
Based
so
on, like,
so
part to part.
sure. So the question is even for electrical, and I'm going to touch electrical in a second. So right now I'm talking about fuel, but electrical is the same thing, right? I don't think I call it fuel selector ratio. I call it power split ratio. Same concept, right? You can actually change where the energy is coming from on the aircraft. Okay, any questions so far? In the back, no questions? All right, cool. So in the next, we have 25 minutes left. I don't think I'll use all 25 minutes, but I'm gonna cover electric aircraft because if you have an understanding of how fuel aircraft work and how electric aircraft work, then if you for those who are developing hybrid networks, the challenge now becomes how do you really merge these two concepts together? Okay, so let's actually look now at the electric aircraft network. So RCAIDE energy networks, all electric, right? So all electric network looks very similar, right? A network comprising of battery packs to power rotors via electric motors on a bus, right? So once again, it inherits from the network class. And let's see what happens here. First, you take off your conditions. So like I said, conditions in the turbofan engine network is usually because you need properties of the atmosphere to compute, the thrust, etc., right? So we need some conditions in here. But instead of fuel tanks, instead of fuel lines, we have buses, right? A bus is equivalent to a fuel line. Make sense? An electrical bus. So we have buses. Now, before I go into this, I'll just say that the electrical network is a little bit more complicated, right? Just the FYI, because you can recharge an electrical network. And the interesting big thing becomes, can you recharge the electrical network in flight, right? Which you theoretically can't, right? So, like I said, when we were thinking about how to code up this network, we thought about, okay, what are the wildest things you can do? And make sure the code can not only do the nominal things, but also any type of performance behavior you want it to do. Okay, so basically, in line 91, as usual, the first thing it does is, because it's a network, an electric network, it has on buses as opposed to fuel lines. So it does a for loop and determines, it first does a for loop to look at one bus at a time, right? So for a bus and buses, right? If the bus is active, it's going to do a whole bunch of calculations, right? Let's minimize this. Else, it doesn't do anything, right? So let's look and see what happens if the bus is active. So if the bus is active, it first takes out some properties of that bus, right? On the bus, you can have avionics. You can have payload on the bus. Sometimes payload draws power, right? And the first thing we're going to do is that we're going to compute how much power does the payload and avionics draw. And this is a parameter set by the user. I haven't covered the X57 yet, but next week, hopefully when I cover the X57, what I did is I defined the avionics item, and I assumed it took 10 watts, pretty much, right? So you compute your avionics power, your payload power, and then it pretty much essentially computes the bus voltage, right? So on electric systems, typically what happens is that electrical components operate on a bus voltage, right? And those electric machines, etc., use the bus voltage to run, right? So basically, we have a bus voltage, right? And then look what happens here, right? you have you have an if else statement, if it's recharging or not, right? Because like I said, the bus itself can actually be in a recharging state or charging state, right? So if the bus is recharging, oops, basically it goes in and looks at for each battery on the bus, because remember the bus is like the fuel line, and in a similar way how I can have multiple fuel tanks, I can have multiple batteries, right? So for each battery, it pretty much computes essentially it puts the parameters of the avionics power and the payload power and how much charging is actually occurring on the bus component. And then it pretty much computes in this line, it runs the bus, right? And by running the bus, you pretty much determine how much energy is the bus actually, how much energy is on the bus and in which direction it's going, pretty much. And once you have that, you append it onto the battery, right? So you append the properties of the bus onto the battery and you run your battery, right? So if you look in line 116, you see that the current is going in, you have your battery outputs, and pretty much in line 16 to 18, you append your components from the bus onto the battery and you run your battery, right? And that line 118, depending on the direction or the value of current being positive or negative, it will recharge and charge your battery, basically. So it pretty much loops through each battery and charges it based on how much charging you set. So if you are doing a simulation where you're charging in Chicago here, right? The value you would probably have to change is what the bus voltage or the current you're charging, and also how you want your power to be split, how you want your charging to be split, to answer your question. And then you pretty much just run the script and it calculates this energy calc pretty much computes the battery energy calculations. That's where most of your scripts live, right? So that's what happens when it's recharging. But for most of the time, it's discharging. So when the aircraft is discharging, similarly, remember in the turbofan network, the first thing we do is to run the turbofan and determine the properties of that turbofan. I mean, of all the turbofans on the fuel line. We're going to do the same exact thing. So there's uniformity with all the networks. So in this line, I would say the most important line in this script is line 120. Similar to how we simulate the turbofan engines, we simulate the all-electric propulsor, right? So if we're to go into this all-electric propulsor, let's see what's in here. It's coded the same, which I probably need to change a little bit, but basically for each propulsor, right, it loops, and if the propulsor index is not 0, so pretty much if it's not the first propulsor and it's identical, this happens. But typically when you go in here, to start with, you calculate pretty much, you start at line 81. So in line 81, you run the ESC, electronic speed controller, then you run the motor. You pass the arguments or the energy, or you do the calculations for the electronic speed controller, which obviously goes to the motor, right? And then once you pass the arguments to the motor, you calculate an RPM. Where do you think that RPM goes? To the propeller or rotor, right? It goes to the rotor. Once it computes that, you can get the thrust, well, force, torque, power, CP, and a whole bunch of other outputs, right? And then you just store the information. And as you can see here, I'm not only storing energy, but I'm storing noise as well, right? I'm storing information for the noise. It's very similar to the turbofan network. It's just electrical components. That's all. And then if you have, let's say, let's say you're doing an aircraft that has a distributed propeller system, right? You don't want to run that 8 times, right? If you have 8 propellers. So after the first one, it just loops in here 7 times. If you say that the propellers are different, it will compute the properties of that propeller but you have an identical flag you can turn on and off, basically telling you if you want to run it 8 times, 7 more times or not. Make sense? Okay, so that's the all electric propulsor, right? So that's line 120 here. Oh yeah, line 120. And once you have all the thrust, the power, and the current on that bus, you can essentially total it to get the total thrust and total power. And then once you have what's the total on that particular bus, right? You can then pretty much go through the batteries and determine based on the battery power split ratio, similar to the fuel selector ratio, how much energy is coming from which battery. Make sense? So now you can have, for the first time, you can model multiple batteries on one bus, right? And then you do your energy calculations. As you can see here, the current, there's no negative sign here, right? Because the current is flowing in the other direction. No, you're not charging, you're discharging. And then once you do that, your script is pretty much done. Yep.
So split ratio is basically an input from the user.
The split ratio is the input from the user.
Shouldn't it be more of a function that decides where the power is coming from or where the fuel is coming from?
Not really, because the user should have the ability, and this is something that is done at the design level, particularly where the energy is coming from. And the split ratio is very important when you're doing stuff that what Edwin wants to do, whereby the split ratio allows us to model systems that have partial battery failure. Suppose half your battery fails on that bus, right? We can model the split ratio whereby you send all the energies come from one battery and the other battery split ratio is 0, which represents the fact that it's not running. So we have some thought in terms of how to model this in a way such that you can model failures as well.
But shouldn't those split ratio be like, shouldn't we have the option of changing the split ratio
Yeah.
midway through a simulation?
Yeah, you can.
Like midway through a simulation?
Yeah, you can. You can do it midway through a simulation. Why? Because you remember when you're modeling an aircraft, and for those, this is the video before. When you're modeling an aircraft, you assign you can assign a different battery config, a different aircraft configuration per segment. You can actually have multiple aircraft configurations and change the split ratio. Or if you want to change it during a particular segment, my advice is probably to either run it in some optimization where you can automatically change it. Yeah, that's probably my suggestion.
Question came because we have, so let's say we have 2 battery packs and one is a new battery pack and the other one is an older battery pack. And throughout the flight, midway through the flight, one battery pack fails,
Yeah.
like in terms of weight. So it needs to learn on its own that there is 0 voltage here. And it needs to
yeah.
change the bit ratio.
That is a more a BMS issue. That is possible, but that's a more, there's some nuance behind that, I would say. It is possible with this code, but your aircraft should know, you should know beforehand. I mean, you're doing it as a designer, but your aircraft should know if the battery is going to fail or not based on some things. If it doesn't, if the battery automatically fails, that if else statement, I guess you could put an if else statement in this code if the battery fails, but that's more of a BMS design, not an aircraft conceptual design type of thing.
Like
Yeah, true. You could also put an if else statement if the voltage passes a certain point, change the split ratio moving forward. I guess that's the way you can.
time step. Every time step.
Yeah, which yeah, I guess it would be every time step, yeah. Yeah.
That means you would be running a test where there's like a random element to it and you don't know when it's gonna fail. I mean, because if you're testing, you know when it's gonna fail, right? Like you said, it is an input. If you want to test when the battery fails,
Yeah.
then you would know exactly when it happens.
I think that real-time failure is something that is, to be honest with you, beyond the scope of this code.
Or you could have like different mission segments and you could consider failure in each segment.
Exactly, that's what the plan is, but to have that
Yeah,
instantaneous failure would be, that's beyond the scope of this code as a conceptual design tool. It could be possible, I mean,
Upon
you can code
instantaneous
it.
failure, you could have something like an optimization script that decides what's the ideal
Exactly,
uh,
exactly, yeah.
sort of split ratio for that battery field.
So the basis of my question was they're using two types of battery cells.
Yeah,
And when we're running a operational feasibility study or something.
yeah,
And one battery pack degrades faster than the other, and at the 900 slide, one battery pack, after an hour of flight, it just goes to zero. It's not a failure, it just discharged completely.
yeah.
So,
I think if the battery pack, if that happens, right, and let's say you have a battery pack that fails, I think as the aircraft designer, I don't think we should fly that flight again. So you just say at that point, the mission is
but
over. You shouldn't fly the next flight, but you should be able to land on that flight, right? Which that's what the battery split ratio is for it, particularly, right? You can change the split ratio to change how much energy is coming per battery.
I think that is something RCAIDE should decide, not the user.
That will be running an optimize. I gotta think about
That's
that.
like an if-else condition, that if the battery life goes below a certain point, rearrange the split ratio so that this battery does not degrade too fast on the very next mission.
Well, that's true. We can. That's just an if-else statement, I guess.
Exactly, and the split ratio can be used for this optimization thing, can be used for a hybrid one as well, if the battery levels go down. This overall split ratio. between
Yeah,
the fuel
yeah.
And the battery favors the.
Good point. No, yeah, I was actually gonna go to hybrid. I was just gonna talk about hybrid nets, but the split ratios, these few selective ratios and split ratios, they really come powerful for hybrid networks, where you actually can now dictate. Now, the question you're asking is, at what level, to what degree does the user do it versus the code itself? I think that's a hard question. How essentially should a user have manual say in when the split ratio happens, power or fuel or both, or should an optimizer do it? That's a great question. My engineering intuition would say optimization, but there are some practical cases where that may not be the case. So I think that's an open design question that I don't want to, I guess, channel the user into making. But there are some things, some fail-safe things that we probably can implement in the code. So I think these are great points. We should definitely look to include all these. Yep. Yes, and good point. I think even that determining of split ratios is very dependent on safety regulations and stuff. So I'm trying to invite some folks from AIAA who I see pretty much every 6 months here who have experience on electrification and certification SAE standards, because those are things we need to really elevate this level of modeling. Right? Okay, so we have 7 minutes. The last thing I'll say about this all-electric network is that, yes, I haven't covered hybrid networks because we're still developing them, but this network was actually able to model a lift plus cruise aircraft. In a lift plus cruise aircraft, you have, at minimum, 2 buses. You have a lift bus and a forward bus that operate at different voltages, right? Because lift propulsors or the rotors operate differently from propellers. And therefore, you can have multiple buses. Like I said, you can define multiple buses on your aircraft. So for the lift plus cruise aircraft that some of you folks have been doing battery noise modeling, I guess battery modeling too, the lift bus has on 8 rotors and 1 battery, and the forward bus has on 2 rotors and 1 battery. And it still accumulates all of the thrust, all of the power, everything here, but basically it splits the power on the batteries that are connected to that actual bus itself. Granted, I guess some folks in here, we're working on rewriting these scripts a little bit such that you can have the ability to channel energy from one bus to the other. But yeah, we're still thinking about how to actually do that Pythonically, but yeah. Yep.
Is it the same battery and that gives power to both buses, or is it a different one?
Same battery giving power to both buses. So it's more challenging, trust me. It's way more challenging than people think it is. I spent quite a bit thinking about how to do that. Anyway, so if there are any more questions, I'll end this presentation right now. Professor Ansel, oh, he's not here anymore. He hopped off. Francesco, do you have any questions?
Too many, but I have to think them through. So
Okay.
I'm good for now. Thank you.
Yeah, just send me an email and I can answer them. We're still developing.
Yeah,
We're still developing this part as well. I think the thing we try to, I guess myself, the thing I try to do is add functionality that was not there in Suave, but I'm sure there are better ways to actually write it. But this code is actually, I mean, we're focusing on the functionality, but I'm sure there are better ways to definitely write this out.
no, I mean, I just have some questions about how some of the physical quantities propagate
Okay.
across, the buses and the energy networks. But okay, I will follow up with you separately.
Okay. Awesome. Yep. Yeah, sure. Yeah. Okay, awesome. All right. Well, I think that brings us to the end of this session. Next week, I think I'm going to look at modeling an eVTOL. So essentially, it's using this same all-electric network where we're going to model a few types of eVTOLs, some using maybe one bus, some using two buses. So I'll see everyone next week.